All right, guys, here we go. This is going to be the final lecture and lecture 19. As you see, let me check. It seemed to work. So, okay. Now, today we're going to talk about maybe, predominantly just to say, how to test stationarity. And before I do so, I need to define what order of integration is. I mentioned this the last time, but this time I will basically try to generalize it. Would you be so kind to close the window, please? Some noise coming from outside, and it's going to be a little bit loud. Anyways, I hope it does work. So, all right, guys. Now, the order of integration is basically. So, when you say, for example, you have a first order or a second order, whatever, this will give you the number of differentiations to obtain or to achieve stationarity for a process. So sooner or later, it's going to be stationary, okay, after a number of differentiations. I'm going to explain this a little bit more in detail. So let's say, for example, let's take the random walk. With or without a drift, it doesn't really matter. I will choose to basically take the random walk with drift to be basically generalizing it. And then you have this structure, okay, so we talked about it last time. Or if you basically subtract yt minus 1 on both sides, you can also express this in terms of its increments. Okay, so that is basically another structure that you're going to see. But I don't want to basically go to that far. I want to basically consider this expression, okay, what I was, substituting yt minus 1 by the corresponding expression. So you have v plus yt minus 2 plus the noise at time point t minus 1, and then you do this basically sufficiently many times until you get back the starting value. Let's assume that basically the process has started at some point somewhere. So this is basically what it would be, okay, and that's the expression that we had last time. Okay, now, since the variance is time dependent among others, so is the mean, by the way, but you could get rid of the mean if you basically just drop the drift. But let's say the variance is always going to be time dependent, and that was basically the structure. Here is the time dependency. The random walk is not stationary, and we have seen this before, right? Okay, so among others, I mean, also there was the autocovariance that was also time dependent, but the major issue was basically with the variance. Now, when it comes to the increments of the random walk, and that's what I want to basically to express here. So how would you get those increments? You just simply subtract yt minus 1 on both sides. So then you have yt minus 1, which are basically the increments. And so that's it, okay? So then you have basically the constant plus the noise. And that's what the increments of the process would look like. And when you look at the increments of the process, then you'll find basically the moments which were, basically corresponding to the moments of the noise plus a constant. So since the noise has the expectation 0, you're going to get back the constant for the moment. And then you have the variance. Now the variance does not depend on additive constants, as you see. This is just simply the variance of the noise, and that's what you'll have. And then you have the autocovariance. Basically doesn't depending on, or not depending on additive constants either. So you have just 0 then, because the noises are uncorrelated. That's it. Now, you have no time dependency regarding these moments. I call them moments here in this case. It's not that long. Okay, so the issue would be then the increments of the random walk are stationary. So after that, so when you have basically this process, which is non-stationary one, if you're differentiating it, meaning that you look at basically at the increments of the process, then you're going to get a stationary process for the very first time. And that will give you the order of integration, because you need to differentiate the process once to get a stationary process for the very first time. And this is basically what the order of integration would be of the process. So we say that the random walk, which is denoted by y, has the order of integration which is equal to 1. So it's going to be an I1 process. That's it, okay? I0 means literally that you don't need to differentiate the process to get a stationary process for the very first time. But not just that, I'm going to come back to that a little bit. A little bit later. I need to just, try to basically to define this, but this is how it's going to be. Okay, so again, so the number of differentiations to get a stationary process for the very first time is going to be equal to 1. So that means that the order of integration of the random walk, so we're talking about the random walk here, okay? We say that the random walk is a so-called integrated process, and the integrated process is basically of order 1, and that's it, okay? Usually there is also integrated of order 0, but in case if the process is integrated of order 0, then we don't say that it's integrated. So if any time you see basically the term integrated, it's always going to mean a stationary process with stationary increments. That's it. Okay, so non-stationary process with stationary increments is going to be integrated of order 1, and this is how it will be. Okay, so this is how we denote this, and I'm going to define that. Okay, so we're going to define this, okay, right in a moment. So again, this is a non-stationary one, and that's going to be a stationary one. If you go further, so we're going to look at the increments of the increments, by the way. You can do that also. All right, so how would you get that? Okay, these are the increments, okay, of the increments, by the way. So this is another differential operator. Now, you can simply just take that, so that's going to be delta yt minus delta yt minus 1, okay, simple as, again, so every kind of process you have, this is how the difference operator works. And after that, when you have that, this is going to be v plus the noise, that's the first one, and minus v plus the noise at time point t minus 1 for the second one. And since you're subtracting it, you find that this is going to be the increments of the noise. You understand that, guys? So that's basically what it's going to be, okay? And that's what I also have it here. And that is also a stationary process, because if a process is stationary, then its increments are also going to be stationary. So if the noise is stationary, then the increments of the noise are going to be also stationary as well. This is not a surprising result, by the way. So that's what you will have here. Okay, now that's it, okay, and that's called basically over differentiation, by the way, because you don't need to go from here to this bar, okay, to get a stationary process, because you have already a stationary process. So that process will be called that one, okay, so the increments of the increments, okay, I'm talking about that. The increments of the increments are going to be over differentiated, and that's the name of the process, by the way. So that's how they call it, because you don't need to differentiate it anymore to get a stationary process. You have a stationary process already, so why would you differentiate it? If you differentiate it too often, then you have a so-called over-differentiated process. I'm going to define this precisely how it's going to be, so then you'll see what it is. But I'm going to use the so-called long-run covariance. You might remember that one, okay? I also displayed the definition of the long-run covariance, so this allows me also not just to consider asymptotics, as I mentioned before, okay, that are involved, but also consider the issue of order of the integration. Okay, now let me start by just saying that the stochastic process is called integrated of order 0. In that case, so in the literature, basically, if a process is called integrated of order 0 or is integrated of order 0, then we don't say that it's an integrated process. So usually, if we say that a process is integrated, then we mean that is basically an integrator of order 1 or higher. But again, this term is also common, okay? So just for you to understand this. Okay, now this is how it's denoted. Okay, so the order of integration is 0 if, and it means that the process is stationary. So you already have to have a stationary process to be integrated of order 0, but just because a process is stationary doesn't necessarily mean that it's going to be integrated of order 0, because it can be also over differentiated. Okay, so a stationary process, or let's say that which is over differentiated, is not integrated of order 0. And how would you basically get over differentiation? How would you quantify that? Because this is something that you can do, and you're going to use the long-run covariance. Okay, so there is going to be a difference between the long-run covariance of a stationary process that is not over differentiated and a process which is going to be over differentiated. Now you might remember what the long-run covariance was. I was mentioning that before when I was talking about asymptotics. Okay, so when it comes to, let's say, ARMA models, for example, and you want to establish essential limit theorem for ARMA processes, you're going to need, among others, the long-run covariance for that. Okay, so it needs to be finite, because if it's not finite, then of course you cannot establish essential limit theorem, among others. And for that to be finite, it is going to be needed. It is going to be stationary. That's also a basic requirement. Now, that was the variance plus 2 times the sum of all covariances, okay, with respect to every time lag there is, okay. Since the process is stationary, it doesn't matter which direction are you moving to. And if you have this expression where it's finite and positive, okay, so then you will have a so-called integrated process of order 0, okay? So keep in mind, guys, that every process which is integrated of order 0 is stationary, but not every stationary process is integrated of order 0. People tend to use this synonymously, and therefore I wanted to basically to warn you guys that it's not the same, okay? So, but again, people tend to use this synonymously. Integrated of order 0 means a stationary process with a finite and positive long-run covariance. That's it, okay? So it needs to be both, because if it's 0, then it's also basically finite, okay? So you have to have something other than 0. If it's 0, then it's going to be over-differentiated. That's what you're going to see. So this is how you distinguish between stationary processes. Either a process is over-differentiated or it's going to be integrated of order 0 if the process is stationary. Okay, so the long-run covariance, among others, is going to be also a tool which tells us, you know, what the order of integration of the process is. But that's what you'll have. Okay, now, the process is going to be called integrated of order 1, which, again, I mentioned before, if the increments are integrated of order 0. Okay, so not just stationary increments, but non-stationary process with stationary increments. So that's how you basically you can say that. Okay, so increments are of order 0. So if basically a process is integrated of order 1, then it's non-stationary. Okay, that's a fact, because if it was stationary, then it's either going to be integrated of order 0 or it's going to be over-differentiated, but that's neither of the case. So the process is non-stationary, but it has stationary increments. Okay, so that's that. All right, because if it has stationary increments while the process is not stationary, then you would need to differentiate the process to get a stationary process for the very first time. So then the increments of the process are going to be just stationary. You understand that concept, guys? Okay, so that's basically, if the increments are stationary while the process is not, then it's going to be integrated of order 1. Okay, and there is a way to test this, and that's what your next assignment is going to be about. Okay, you're going to get the series, and then you're going to figure out whether the process would be coming from a stationary process or not, or the observations would come from a stationary, or which were generated from a stationary process or not. That's what you would need to do. Okay, but I'm going to be more specific when I talk about that, but that's not that. So that is involved. Okay, so because that's a huge issue in time series, and I want you to do that at least once. All right, now what about basically higher order? Okay, so let's say if it's integrated of order D or so, D can be equal to 2, for example. So if it's basically equal to 2, then this means that the process is not stationary. Okay, and then you would need to differentiate it twice. So the process itself would not be stationary. Okay, so that is non-stationary. All right. So is the increments of the process are still not stationary, okay? But the increments of the increments are going to be, okay? That's it. So this is how basically how it is, okay? The process itself is not, increments is not, but so is basically the increments of the increments, because that is the first time you will get the stationary process, okay? So therefore, you can say that the process is integrated of order 2. Okay, usually you don't have basically, I mean, you don't go that far. Okay, so most of the time it's integrated of either of order 0 or 1, maybe 2. Okay, but in empirical literature you don't go beyond that most of the time. There are exceptions though. Okay, but let's say 90-95% of all cases you don't have a high order when it comes to integration. So maybe integrated of order 2, but it does not go beyond that. Again, so 3 or 4. I haven't seen basically in empirical literature a time series that is integrated of order 4, to be honest. Not yet, but maybe there is. Okay, so it's either 1, 2, or 0 most of the time, but actually it's either 1 or 0. These are the two. All right. Now, anyways, okay, so then you have basically a process which is over differentiated if the process is stationary. Okay, so that's number one. And it has a zero long-run covariance. Okay, so keep in mind basically that the long-run covariance of an integrated process is positive but finite, whereas the long-run covariance of an over-differentiated process is going to be zero, and that is also true in the other direction. So if the process is stationary and the long-run covariance of the process is zero, then the process is going to be over-differentiated. And if its long-run covariance, in addition to stationarity, is positive but finite, then it's going to be integrated for a zero. You understand what I'm saying? So it could be actually called also integrated of order -1, right? Because then you, or -2 or whatever, so it's way more than over differentiated, but that's how it is. Okay, so if it's over differentiated, then we don't care basically what the order of integration would be, but it would be negative, so that would make sense to assign a negative order to it when it comes to the integration of the process. You understand that? So I'm going to demonstrate this, guys, so because you might not be clear, you know, what has something to do, what has the basically order of integration has to do with the long-run covariance, but I'm going to talk about it. So this is how it would be. So that's a formula you might remember, and we were considering an MA1 process. Now, moving average process of order 1, this is how it would look like. So that's basically the structure of the process, okay? And that kind of resembles the processes that we were looking at. So when it comes to, for example, but I would just basically add the variance and the autocovariances to it. So the variance was 1 plus b squared times the variance of the noise. We were seeing that. It's not difficult. Basically, the variance of a sum is the sum of the variances. It doesn't depend on additive constants, so you have the variance of the noise times 1 plus b squared, because if you want to take out the multiplicative constant from the variance operator, you need to square it. Okay, we were talking about that weeks ago. Okay, I'm not going to do that anymore, but that's how it was. And then, of course, you have the autocovariances, and there is something which is called finite memory. So if the order of the process is greater than 1, or basically the lag order of the autocovariance is greater than 1, sorry, because the order of the process is equal to 1. But if basically the order, when it comes to the lag order of the autocovariance is greater than 1, then it's going to have 0 autocovariance. So that's how it was. And if you want to calculate the long-run covariance, you simply just take the variance plus 2 times the total sum of the autocovariances. There is just one expression which is not 0. The other one is 0. And so this is how it was or would look like. Okay, so that's how it was. And of course, this is basically B1, where B is the lag polynomial. So you might remember basically what the lag polynomial was. The lag polynomial was 1 plus B, let's say L, and then if you put basically 1 in there, you're going to have 1 plus B, and if you take the square of it, this is 1 plus B squared. But that's just a different notation. That is also true basically for higher order moving average processes, by the way. So it kind of generalized that expression. So if you look at the second order, third order, whatever, that's how it would be. But you don't need to consider that now. Okay, so that's basically the general expression when it comes to that. So this allows me basically to do that. Okay, now, but that's not what I was talking about. Okay, the issue was with the random walk, because I wanted to look at the long-run covariance of these processes. Let's start with the random walk first. Okay, now the random walk is non-stationary, right? So if it's non-stationary, then why would you basically examine whether the long-run covariance is finite or not? It's not going to be, by the way. So if you look at the long-run covariance of the random walk, you'll find that this is not going to be finite. You'll find that it's not going to be finite. But that's something that I want to skip for now, okay? What I'm interested in is the increments, because the random walk is or was integrated of order 1. Okay, so this is how it would look like. And this is a moving average process. So if you see that, okay, that kind of resembles the moving average process, because if you look at the moving average process of order 1, okay, this is, or that's, or let's say, let's call it Z, because, you know, it kind of looks, if you call that zap, this is how it is. So you have a constant plus the noise plus b times the past of the noise. And if b is equal to 0, okay, so if this is equal to 0, then this is going to be the increments of the random walk. You see that, guys? So that's basically the increment. This process is then the increment of the random walk at time t. You see that? Okay. So then, of course, but that doesn't prevent me to look at the autocovariance. So if b is equal to 0, which it is in this case, then the long-run covariance of the process is just going to be sigma squared, obviously. Okay, so that's not a big surprise. But anyway, so that's what I'm going to look at. Okay, so if basically the moving average process with of order 1 with b being equal to 0, that resembles basically to the increments of the random walk. And then if you would do or consider that, then you simply just put 0 in there, and then you'll find that the variance is going to be equal to sigma squared, the long-run variance. So the long-run variance of the process is equal to the variance of the noise. And since this is finite, of course, by definition, and greater than 0, then you'll have that the increments are going to be integrated of order 0 then. Okay, so that's basically what the major result is. Finite and positive long-run covariance with a stationary process would generate a process which is integrated of order 0. Okay, is that clear? All right, so again, by definition. So that's basically what it is. Now, if I look at the increments of the increments, by the way, and that's what I was talking about, which is also a stationary process, but it was over-differentiated. Now, why is it over-differentiated? Because it will have a long-run covariance that is going to be 0. So if you look carefully, guys, this resembles, and then I would just basically try to put that regarding, a moving average processor for a common denominator. Let's call a moving average process Z. Then you have a constant plus the noise plus b times the past of the noise at time point t minus 1. Now, if b is equal to negative 1, then it will be basically that structure. So that is going to be basically the increments of the increments then. Okay, so b is equal to negative 1. So if basically I take that, okay, so where the increments of the increments are following a moving average process where the only parameter that is going to be involved in here is going to be equal to negative 1, then if you put negative 1 into the long-run covariance of the moving average process, you'll find that it is going to be equal to 0 then. So 0 is the long-run variance of the process where you have a stationary process with a 0 long-run covariance, and that will basically, by definition, generate an over-differentiated process. So that is the reason why the process is already over-differentiated. I was basically explaining that intuitively. So if you start from here and you're differentiating it, then you already get a stationary process. But if you differentiate it again, why would you basically do that to achieve stationarity if you have already achieved stationarity before? So that doesn't make sense from that perspective. But that confirms the result. So the long-run covariance allows you to distinguish between stationary processes where the process is stationary with a finite and positive long-run covariance, or where a process is stationary with a 0 long-run covariance. If the process is stationary with a 0 long-run covariance, then the process is going to be over-differentiated, just as the increments of the random walk are. Yes? Then it's not going to be stationary anymore. Okay? That's... No. I mean, you cannot. I mean, the issue is what you want to do with that. So maybe you do co-integration testing or whatever. If basically you have to have a stationary I mean, every process has to be stationary in order to basically for the vector autoregressive model to be considered stationary. If the first two are stationary, why would you differentiate them? Yeah. Yeah. Yes, but you have an ARIMA model then. So if one is not stationary, but the other two are, then you have, this is called the ARIMA model process. So ARIMA, and that's exactly it, okay, means literally that this is an integrated ARMA model, okay, usually integrated of order 1, okay. I'm not sure whether the model, the specification regarding the model does allow you, okay, to basically to just, you know, take that process out, differentiating and put back into the model, because it might be the case that from the economical perspective, it doesn't make sense, okay? But let's say if y, let's say follows, okay, so if y follows the ARIMA process, which is a non-stationary ARMA model with integrated, where basically mostly the process is integrated of order 1, then it is the case that the difference of the process, whether it's multidimensional or not, it doesn't matter, would follow a stationary ARMA model, okay? So I'm not sure if whether you can basically just take out single components of the process, differentiating them, and put back in regarding the economical context that you're in. So that would probably also depending on the economical constant, but that statement is true. So if y follows the ARIMA model, whether it's multidimensional or not, because if there is one component which is non-stationary, then it's going to be integrated of order 1, period, okay? So it doesn't matter, okay, because when, I mean, that's how you do it, you know? So if it has 3 components and you put salt in one, then and you combine it, all 3, then it will have salt in it, no matter what. So you cannot take that out probably. But if, let's say, y follows, let's say, multidimensional ARIMA model, which would be the case as what you described, then it's different, okay? Whether basically it's vector, autoregressive or not, would follow a stationary ARMA model. That's the case. Then you have a over-differentiated processes in there, but it doesn't matter. Okay, that's how it would be. Okay, I think, but I'm not sure regarding the economical context. So how would you basically consider it? Whether you would try to find it or not, that's a different issue. Okay, if you look at samples, single samples, and you split them from each other, then you can simply just say whether the process is stationary or not from the empirical perspective. You don't need to put them back together, actually. But I can imagine that there is issues regarding it, because most of the time, either all processes are stationary or all processes are integrated, you know. Why would you combine a stationary process with an integrated process, by the way? It doesn't make much sense to me. So again, it depends on the context that you're in. Okay, but sometimes it's not ambiguous, especially from the empirical perspective. How would you consider it when it comes to basically the model? Okay, so it must make sense from the, let's say, from the theoretical perspective before I would just, you know, try to take it out and put it back in, whatever. Okay, is it clear, more or less? So again, it's not an easy question to answer regarding it. I can imagine that there is going to be issues, but most of the time, the processes that are involved are either all integrated or not, okay? That's how it would be, okay? Anyways, okay, so if there is one process which is not stationary, then everything else will be messed up a little bit regarding the estimation, okay, for example. But I would just basically consider. Now, this is, again, but the long-run covariance is illustrated, allows us to identify over-differentiated processes from the theoretical perspective, okay? So if it's stationary, with a 0 long-run covariance, then it's going to be over-differentiated. Anyway, okay, now there is the concept of spurious regression, which I want to illustrate. That's a huge issue, guys, a very important one, okay? This means that you have, from the empirical perspective, most of the time, you find significance between two processes which doesn't exist, actually. So let's say if the two processes are both integrated of order 1, not integrated of order 0, so both are basically non-stationary processes, or it is also true if the order of integration is even higher. And if they are independent in addition, so keep in mind, guys, there is absolutely no relationship between them. And then you would consider a regression model, which looks like this, where basically y is the response and x would be a predictor. Okay, so u is the error term, by the way. Okay, so let's say you have some error term, and that's not the model that is basically underlying here. Keep in mind, guys, it cannot be. So this is not true, okay, because the things are independent, okay? Otherwise, if it is true, then it would be. But then if you consider that and try to estimate things, you know, by using OLS regression, so you can run an OLS regression, and you find that the coefficient determination, okay, is going to be moderate to high, or let's say basically I'm talking about the test statistic. So you estimate, you try to test the significance of this parameter for which you would calculate the test statistic. How? Okay, so the test statistic is actually the estimate minus 0 because you test 0. Okay, so that's the test statistic that I'm talking about. You test for significance, and then you would basically consider the standard error of that estimate, right? So the standard error is the estimated standard deviation. You might remember what that was, right? So the formula basically for the standard, you don't need to write it down because we were running OLS regressions. That was actually one of the first 2 lectures, right? And the standard error was the standard error of regression times, if I recall it correctly, I'm not sure, 1 by the square root of n times the empirical variance, which I called Sx. I think that was the formula, but I'm not sure. And the standard error of regression was 1 by the degrees of freedom, which is n minus 2 times the residual sum of squares, and then you would take the square root of that. So that was the formula. Again, check that out, guys. This is basically how you would calculate the test statistic, by the way. Okay, so that is also a random variable if there is no samples involved. Okay, so that is random. Okay, now what you find here is that the test statistic does not converge, or let's say the absolute value does not converge, or it diverges, to be basically to precise, as the sample size increases. So that means that the greater the sample is, the greater the test statistic would tend to be. Okay, again, it diverges basically, so that's how you say it, almost surely, with probability 1, okay? So that means that basically the probability that the test statistic is equal to infinity, or so it does not converge, okay? It diverges, right? It's going to be equal to 1. This is basically the concept. You might remember that, all right? So that was basically it. Or, I mean, you could call it the limit here, but that's what I was expressing, okay? So as the sample size increases, all right? Now, the consequence of that, since the absolute value of the test statistic does not converge in distribution, and it does not converge in probability, right, either. I mean, that would not be the case. But anyway, this means that the test statistic basically, I mean, diverges as the sample size increases. So it goes, I mean, the absolute value, of course, because, you know, doesn't matter whether it's, you know, the relationship that you would estimate would be positive or negative between the two. So that means that the null hypothesis that the parameter is not significant would be rejected with probability 1 as the sample size increases. So as, I mean, of course, there is no such thing as infinite number of observations, right? So that is a theoretical concept. But as the sample size grows, so does basically the probability of rejection. So the rejection rate, there is papers involved. You know, the first paper came out was in 1974, based on a Monte Carlo simulation by Granger, by the way. I think that was the first one. Okay, their rejection rate was, I can't remember, call it correctly, 70–80% of the time. Anyway, so it depends on basically the specifications. However, although the processes are independent, the null hypothesis is going to be rejected with probability 1 as a sample size converges to infinity, or diverges basically, or approaches infinity. You understand that, guys? although there is no relationship between the two. Okay, and that is a huge issue, guys. So therefore, one of the reasons basically why stationarity is so important, or testing stationarity, okay, in practice, from the critical perspective, is so important. Okay, and yeah, so that's it. Okay, right? So you would basically, you find that there is a relationship between them, although there is not, with probability 1, let's say, as basically the sample size increases, which is not true, by the way. There is no relationship between the two. Okay, so as soon as basically there is non-stationary processes involved, you cannot take that basically into consideration within a simple OLS model. So that's basically not what you will have. Now the process is called trend-stationary. Okay, that's a concept we haven't addressed before. Around the linear trend, which is basically a linear function of time, as you see. So that is a function of time, which is a linear function. Okay, so there is a slope and there is an intercept, so that means there is a linear trend in the data. That's what basically what I was talking about. If you would consider basically the process to be like this, okay, so if you have the linear trend, okay, and then plus a stationary process, it's not necessarily a noise, so let me call it E. Okay, so E is a stationary process to which basically a linear trend is added. Then you would not argue that the process is integrated, so then you would basically rather say that it's stationary around the trend, meaning that if you take the process, okay, and you subtract the trend, so you take out the linear trend from the data, then you would get a stationary process. Okay, so then you would have a stationary process without the trend. You understand what I'm saying? Okay, so that is basically what trend-stationarity is, which can be basically expressed by the following expression. Now keep in mind, guys, this is not a noise. Okay, that is just basically a stationary process. Okay, it can be a noise, of course, because a noise is stationary, but it's not necessary to be a noise. Okay, some sort of a stationary process. It can be maybe an ARMA process. So let's say if it's an ARMA process, okay, but it's stationary one, then this process would be a trend stationary process. So if the trend was linear trend was taken out from the consideration, then you would get a stationary process back. So if you want to see a path of a trend stationary process, here it is. Okay, clearly see that this would be the linear trend, by the way. Okay, so if you would take that out from the data, you would find that the process evolves, let's say, around that, for which basically the mean and the variance would be constant. I mean, at least it appears to be a trend-stationary process. This is a typical structure of it. Okay, you understand that, guys? Okay, so if the trend was constant, by the way, then would be already stationary, because the mean, as you see, the mean of the process is depending on time. All right, that's basically it. So there are 3 types actually in practice. Four, let's say. Okay, stationary processes, there are 2 of them: over differentiated or integrated of order 0. These are the 2. There is integrated of order 1, maybe 2, maybe. Okay, but again, even that is not very common. So 1 or 2, integrated of order 1 or integrated of order 2, and trans-stationary processes. And that's it. That's pretty much it. Okay, so again, to be honest, I cannot recall a process which was integrated of order 3 in an empirical study. Maybe there exists, but again, so I cannot recall it, to be honest. Maybe I have to check. Okay. But it's actually in practice, it's either 0, 1, or 2, over differentiated or trans-stationary. These are the types. All right, so there are some of them, as you see, but again, you need to basically distinguish between the 2. This could be, if you don't watch carefully, this could be also an integrated process. So again, if the observation, the sample size is not sufficiently large, then you would not recognize it basically from the path, what it was generated from a trans-stationary process or an integrated process in general. Now, in order to distinguish between those, there is testing stationarity. Okay, so Dickey test is one of them. Okay, there is basically the tests are involved. Usually it's called the augmented version, so ADF test. If you Google it, ADF test, that's the term. Okay, and I want you to implement this with, a specific data. Usually either you take the data that you were writing your papers about, or you would take the data, the fictive data that I would give you, either of the two. Okay, so I will let you decide. This is going to be an optional, but I want you to implement this. You can Google it, and you can basically use packages already, so you don't need to do the programming on your own. Okay, that's something that you don't need to. I will be more specific when it comes to the assignment later on, but I want to explain how it works, because it's not that ambiguous. Okay, so you will get confused. So I try to basically structure it, but you can read that also in my script, okay, which I would basically tend to publish. So there is 3 types, okay, and we're going to start from behind. Actually, I'm not sure why. Okay, so model 1 is going to be the biggest one, and model 3 is the smallest one. So we'll start from behind again, but I'm not sure why. It doesn't really matter. Who cares? All right. So anyway, so there is the first order autoregressive process without the constant. So keep in mind basically the constant, which is usually there is 0. If the process is stationary, so if basically y is stationary, then you might remember, then the formula for the expectation was, you might remember this, v divided by the Lac polynomial of 0.1, but since v is equal to 0, this is going to be equal to 0 then, okay? So if the process is stationary, it's going to be stationary around the mean 0. This is model 3, guys. Okay, there is other, but that's one option, okay? Now, again, so just take it as is, okay? Why and why not, and you'll see later on. Now, there is a reparametrization, which I'm going to perform here. That's not the one, but I just basically write it down as it is. So that's the same as here, nothing special, okay? But what I want to have is basically, instead, I want to have the increments, okay? So if you want to have the increments, you would need to subtract yt minus 1, on both sides, right? So because if you subtract yt minus 1 from yt, then you would get the increments. You understand what I'm saying? But if you do that, you have, in this case, a times yt minus 1 minus yt minus 1 plus the noise. That's what it's going to be, okay? And then you have actually a times yt minus 1 minus 1 times yt minus 1 yielding a minus 1 times yt minus 1 plus the noise. Okay, so that's what it's going to become. Okay, and that is a structure that I'm keeping here, so that is what it's going to be. So if you want to take the increments, that's going to be the result. All right, so and in this case, I'm calling this parameter to be equal to phi. Okay, it has nothing to do with the normal distribution, but it is simply just a new parameter. And the issue is that in this model, okay, so you can basically take either, it's here, just sorry guys, okay, so you either estimate this model, okay, or you would estimate this one, okay, this one, where you have basically the increments. So in this case, the increments are the responses, and then the lagged observations are the predictors. You understand what I'm saying? It doesn't really matter whether you estimate the first or the second type. You can also estimate the first type. You will get just different parameters then, because you can convert these two. So if you have this parameter, then you can just simply subtract 1, and then you would get this one. You understand what I'm saying? So that just basically, convertible from one to the other. It doesn't really matter. You understand what I'm saying? So I remember basically you estimating AR1 models or AR models. I'm not sure, when basically that was your first assignment. Simply subtract 1, and then you will get the other parameter. You don't need to repeat that estimation, actually. Okay, but that's going to be equivalent. You see this for yourself, by the way. Anyways, so that's what I was basically mentioned. So the two models are not the same, okay, because the parameters are not the same. The two models are equivalent. You understand what I'm saying? So if you know one, then you automatically know the estimate of the other, and vice versa. You know, so that's basically what it's going to be. Anyways, okay, so the process is stationary. You might remember this. If the absolute value of A is going to be less than 1, that was a stationarity condition for an AR process. And this is going to be equivalent. So if you basically say, okay, A minus 1 is equal to phi, so then you would argue that phi is equal to A plus 1. All right, so you would just basically replace those, okay? And that's basically what you would have, or you can also say A equals, let me repeat it. A minus 1 is going to be equal to phi. So if you solve this equation for A, you would have phi plus 1, and then you would substitute in here, and then you solve this inequality, and if you solve this equality, you will find that phi would be basically between -2 and 0. Okay, that's just another expression for this. And the process is integrated of order 1, you might remember that, if it's a random walk. So if basically A is equal to 1, and if A is equal to 1, then phi is equal to 0, right? So then, because then you would get the increments basically of the process to be equal to a noise. Okay, so 0 times the path plus the noise yields a random walk, and the random walk, as we basically said, is going to be an integrated process. Okay, now this is basically how it is, and A being equal to 1 is equivalent of phi being equal to 0. You understand what I'm saying? So you can basically just take that, and that's why I like this model, okay, because you simply just test the significance of the parameter phi. Now, testing the significance of the parameter phi is equivalent to testing basically the parameter A to be equal to 1. You understand? So if A is equal to 1, then phi is equal to 0. Right? So it's actually more practical to test the significance of phi than rather testing basically A, whether A is equal to 1 or not. You understand what I'm saying? Because it could be also equal to -1. And then you would also, not having stationarity, whatever. Do you guys get that? Okay, so that's basically how it is. Okay, now, in that case, the process will be integrated of order 1. These are the two options. Now, if A is greater than 1, or the absolute value is greater than 1, then the process will be explosive. Okay, so if you try to simulate something like this, this would basically grow exponentially. Okay, so you would see that from the path. So this is taken out from consideration. Okay, that case where you have I don't know whether you call the process explosive or not, but it's going to be exponentially growing. So you consider it for yourself. It's a non-stationary process which is explosive, and then that would not even be integrated for the 1. So you would differentiate it as you like. It doesn't. It would not change. You understand that, guys? So that's not basically what the issue is. So that is taken out from the consideration. So these are the two processes. Now, if this is the case, then we say that the process has a unit root. Why? Because 1, okay, is the root of the lag polynomial. So if you basically take the lag polynomial of the process, okay, which is equal to 1 minus AL, you might remember that, okay? And if you put 1 in there, then you would get 0, obviously, okay? If this is the case, though, right? So we say if A is equal to 1, then this is going to be the case. If A is equal to 1, then 1 is going to be a root of the lag polynomial. You understand what I'm saying? So if we say 1 is the root of the lag polynomial, this means that y has a unit root, okay? Unit basically to be equal to 1, okay? So that's the expression, unit basically, then this would be the case, okay? So this is a one-to-one relationship, guys. If 1 is a root of the process, then A is equal to 1, and then if A is equal to 1, then 1 is a root of the process. But this is how you say it, okay? So if you say the process has a unit root, this means the process is integrated of order 1. That's it. okay? But I want you to basically to explain, I want to explain where the expression, you know, having a unit root would come from. Does that make sense? Okay. All right. So yeah, and then again, so this is basically what I was saying. So one is a root of basically y's lag polynomial. Okay. And then if one is a root of y's lag polynomial, this means that that a is equal to 1, of course. And if a is equal to 1, then the process is integrated for 1. That's it. Okay. So that's basically these are the two. These are the cases that are involved. All right, guys? And as you see, okay, and that's what basically what I want to mention here, this is going to be the null hypothesis of the Dickey-Phillips test, okay? So phi being equal to 0, as you see. So we're going to test this for significance, because if it is significant, okay, in that regard, then, you know, it's going to be negative. If it's not negative, then the process is explosive, right? So that's taken out of the consideration. So it's either 0 or negative. And that is going to be the alternative hypothesis. So there is going to be a one-sided test is involved, okay? And the issue where phi is even less than negative 2 is also taken out of consideration. Okay, that's not going to be an issue anymore, because if that's also the case, that the process is also explosive. All right, so phi is either 0 or negative. And everything else is basically just dismissed. You understand what I'm saying? If it's equal to 0, then the process is a random walk. All right? And if it's not, then the process is going to be stationary. The third case where the process is explosive is taken out of the consideration. You would not test this anyway. Okay, so when you look at the path of a process, you can, and you would see that the process is explosive, you would not test for stationarity, guys. Again, try to simulate. I want you to experiment, okay? Try to simulate a process for which A is strictly greater than 1 or strictly less than -1, and figure out how it would look like. Okay, so that, again, that issue is taken out from the consideration. All right, so these are the hypotheses involved, and yeah, and that is what it's going to be. So the null hypothesis would say that the process is a random walk. Okay, simple is, because then the increments of the process are going to be expressed by the noise. These are the increments of the process, so then if you integrate it, then you would get back the random walk, as we stated. Okay, so that is the null hypothesis, and then it means basically integrated of order 1, technically, then it's a random walk, okay? And then it has no drift, okay? So in this case, it will have no drift, and the alternative hypothesis is that y is stationary. Now, if I say y is stationary, that is unspecific, okay? Because it would be that y is not stationary, y is stationary, sorry, around the mean 0. Why the mean 0? Because this is what model 3 is, actually. You know, the constant that is involved is 0, okay, by definition, because then it will have a different distribution if it's not. So if the constant is not 0, it will have a different distribution. Just I want you to basically to be aware of this. All right, guys. Now, again, so I'm going to continue. All right, so that was basically model 3. Okay, these are the two alternatives. Either unit root process, okay, so you say unit root, okay, or stationary around the mean 0. These are the two, basically, the two hypotheses. If it appears to be stationary, but not around the mean 0, then you would choose a different model. So these are the two options that you will have. For example, when you basically you look at, let's say, increments, okay, of interest rates maybe, right? Could be stationary around the mean 0. So you will need to look at the time series, whether you know the path, whether it is consistent if the process is stationary, whether it is it could be the case that it is stationary around the mean 0. That's going to be model 3. Now model 2, there is another one. There is a constant there. Okay? So if it's stationary, guys, then it's going to be stationary around a mean where the constant is involved. So that means this is, since this is not zero, it's going to be stationary around a non-zero mean, guys. You understand? Okay, so that's going to be the second type. But everything else will be the same. So now, if there is a constant in here, that is also a constant in here, because just because you subtract yt minus 1 on both sides, it doesn't make the constant disappear. Okay, so there is a constant, okay, in every single expression, but that's that. Now, there is a reparametrization, and the reason why there is a reparametrization, guys, is because you want to make sure that the null hypothesis would also guarantee that, you know, parameter phi is involved. So if parameter phi is also involved, then you would basically, it's enough just to define one single null hypothesis. Okay, so that will be the same, okay, because that will basically drop out from the model. So if basically the null hypothesis is true, then there is no constant anymore, but a is equal to 1, okay, or phi is equal to 0. Again, so it depends on how you're looking at it. Okay, so these things are not involved anymore. Okay, so that is also disappearing. So for the increments, you'll have that there is just basically equal to the noise. So if the increments are equal to the noise, then the process is a random walk, and that was the same null hypothesis as before. But this time, and that's going to be the second type, there is as far as the alternative is concerned, there is stationarity, but around a non-zero mean, guys. So since basically m is not 0, you know, that would be an alternative. Whether you choose model 2 or model 3 depends on the alternative. You would need to ask yourself, if the process is stationary, okay, is it around 0 or not when it comes to the expectation? And if it's clearly not 0, okay, then you would basically tend to choose model 2 instead of model 3. You understand that, guys? So that is basically how you would distinguish. How would you distinguish between these two things? So, and there is model 1, and that is a linear trend here. So there is a linear trend. Okay, you understand? Okay, so that is going to be also related to phi, and then if there is linear trend here, that doesn't disappear in this case, and that would not disappear here in the latter expression either. Okay, so you have the increments as the response, plus the linear trend, plus the lag version of the process, and then plus the noise. This is how you would explain it. Okay, now if phi is 0, which is still the null hypothesis, so the null hypothesis doesn't change. If phi is 0, that disappears. Okay, and then you'll have a linear trend plus a noise. What does that tell you? That would basically tell you that the process is, and that you will see, trend stationary. You understand what I'm saying? Okay, in this case, right? So, but that's just basically it. All right, but anyway, so the issue is you'll have, and you need to understand here, okay, so that's, but that's not what it's going to be, because there is also reparametrization. Sorry guys, so what I was telling was wrong. But there is trend stationarity involved. That would be the alternative hypothesis. You're going to see that later on. Okay, now, there is a reparametrization regarding a new parameter here. So both basically keep in mind that m is the intercept of the linear trend and d is the slope of the linear trend. And both contain phi, respectively. So if phi is equal to 0, okay, which it would be the case, all right, then all you're left with is a parameter delta, okay? Okay, that's what you're left with. So m is going to be equal to delta if phi is equal to 0. So if phi is equal to 0, then this implies that m is going to be equal to delta. You understand what I'm saying? So that's basically according to these reparameterizations. Okay? Now, this means, okay, then you'll have, under the null hypothesis, look up here. Okay, so these things are 0, that is 0, and m becomes delta then, due to the reparameterization. And since if phi is equal to 0, then a is equal to 1. So that is going to be a random walk with a drift, guys. That's going to be the null hypothesis. I apologize. Okay, so here it is. So then this time it's going to have a drift, and the drift parameter is going to be delta. And that's it. And the alternative is going to look like this. So then you say that the alternative would basically conceptualize a transstationary process along the linear trend, where the linear trend is m plus d times t, because if the alternative is true, the process is a stationary one around a linear trend. So, I mean, it's not stationary if it has a linear trend, but if you take out the linear trend, then the process would be stationary. That's it. Okay? You understand it? And for every single model there is always going to be the test statistic. We calculate the test statistic for phi and test, basically, literally speaking, the significance of phi using RT test statistics that you know from simple linear regression, by the way. That's the reason why I was basically calculating it, okay, with you. All right, so, but again, that's what it was. Anyways, so I want to summarize, because what model you choose depends basically on the path of the time series that appears to be. Okay? The null hypothesis for model 3 was that the process has a unit root, which means that the process is a random walk without a drift, basically. Okay? Literally speaking. Integrated of 4 to 1. It has a unit root, right? The alternative was that it's stationary around the zero mean. Basically, for model 2, the null hypothesis was that it has a unit root with the drift. So these two null hypotheses are equal, right? But the alternative is different. So here you have non-zero mean, whereas for this one you have zero mean. Which one you would choose depends on which alternative might be consistent with the data. So if the process, let's say, that you have is a stationary one, let's say it is, or let's say the path that you're looking at it could be coming from a stationary process, all right? Okay, then the question is whether it evolves around a zero mean or not. That's the only issue. So this is how you decide whether you would take model 3 or model 2 into consideration. You understand? Okay, so you're not supposed to basically to pick the wrong one. Again, basically, in doubt, you would rather choose model 2, because then you might consider the expectation of the process. Okay? But there is a price to pay, okay? Because if you omit that, then you have omitted variable bias, and you might know. All right, now as far as model 1 is concerned, the null hypothesis was that it has a unit root with the drift, okay? Now the issue is, again, so in practice, and I want to basically talk about the alternative also, transstationarity. You cannot distinguish, I cannot distinguish, if I look at the path, whether the process is a integrated process with a drift or without a drift. Okay? Because the variance of the random walk is relatively large. So I can only see the difference if you basically generate the same noises. Other than that, again, so since the variance of the random walk is time dependent, I don't really see the difference. So if I see a path, I cannot recognize whether it appears to be a unit root process with or without a drift. Okay, to be honest. So you go by the alternative. Which alternative, okay, might be consistent with the path that you are observing regarding the data? You understand what I'm saying? This is how you select it. So look at the alternative, guys, and ask yourself, could it be the case that the process is transstationary, yes or no? And if it's transstationary, pick model 1, period. Or appears to be or could be the case. Okay? It doesn't really matter. So you can recognize a transstationary process. And if it's stationary, just ask yourself, or it appears to be, whether it revolves around a zero mean or not. Okay, that's the issue. All right, now, the test statistic is always going to be the same for every all single one of them. That's simply just a t-test statistic that you know. This is the standard error, okay, of basically of phi, you know, right? So that's the standard error of this parameter, and we basically consider it how to calculate it in even in the multiple setup. So you know how it works. Okay, guys. Then, all right, we reject the null hypothesis if, and that's it. This is a one-sided test, guys. Okay, because the null hypothesis always says that phi is equal to 0, and then the alternative says that phi is less than 0, right? You might remember that. Okay, so that's what it was. Okay, so that is a one-sided test, and that is actually a left-sided one. A left-sided one. Okay, so you reject the null hypothesis if the test statistic is less than the corresponding quantile of the so-called Dickey-Fuller distribution. So there is a new distribution involved, okay, which is a systematic one. This is a non-degenerate distribution, okay, but that's not the normal distribution, okay, so this is not the normal distribution, in particular not the standard normal distribution, because as you have guessed, all right, the test statistic does not follow the normal distribution. It does not satisfy the central limit theorem, by the way. Okay, so that is no way to establish that. Okay, but that's just basically what I wanted to mention here. Okay? All right, now, the critical values are going to be different. So if you want to express basically the critical values, I usually take the 5% critical value. Okay? For model 3, the critical value, the 5%, just focus on the critical value, is negative 1.94. Now, the critical value of the standard normal distribution, okay, the 5% critical value is negative 1.64, exactly, if I recall it correctly. So the issue is, if you use the standard normal distribution as a reference, okay, you're going to reject the null hypothesis way more often. So you would basically establish stationarity, although there is none. That's the issue, okay, that corresponds basically, especially basically rather to the 10% critical value, but I'm not sure. You understand what I'm saying? Negative 1.96, guys, is the 2.5% quantile of the standard normal distribution, not the 5% quantile. Keep in mind this is a one-sided test, not a two-sided one. Okay? So again, if you use the standard normal distribution as a reference, you're going to reject the null hypothesis too often. Okay? So you're not supposed to. It kind of looks like the normal distribution, the Dickey-Fuller distribution at the first sight, but it's shifted to the left. Okay, so since it's shifted to the left, okay, and if you use the standard normal distribution as a reference, you're going to reject the null hypothesis, even if you shouldn't have. Anyways, so the critical values of the second type are even more shifted to the left. Keep in mind, negative 2.9 approximately is the 5% quantile of that Dickey-Fuller distribution. So keep in mind, this is another version of the Dickey-Fuller distribution, guys. So whether you basically use a constant or not, it has a huge impact on the distribution. Usually it's also generated. So I recommend you use packages when you implement this. Okay, so negative 2.9 is the basically 5% quantile of the Dickey-Fuller distribution. Again, I'm going to put the standard normal distribution next to it. I cannot recall what the 1% quantile of the standard normal distribution is, but that could be also somewhere too, anyway. So if you look at the standard normal distribution, the 5% quantile, if I recall it correctly, is approximately negative 1.64, but I'm not sure, okay, just in comparison. So let's say if the test statistic was equal to, I don't know, negative 1.8, okay, let's say, just for the sake of a matter, you would reject the null hypothesis, because if you use the standard normal distribution, you would reject the null hypothesis because it's less than the 5% quantile of the standard normal distribution. So you would establish stationarity, guys, okay? But you would establish it way more often than it should, because the critical value is negative 2.9 and you have negative 1.8. You understand what I'm saying? So if I look basically that from the perspective of the second model, that is a huge issue, guys. So you're not supposed to take the normal distribution, because if the process is not stationary, it does not satisfy the central limit theorem when it comes to the sample mean of the process, among others. Okay, that's a different story. I wasn't talking about asymptotics where the random walk is involved, but that's what I want you to basically to be aware of. Okay, so you're not supposed to do this. If you use your assignment, guys, you can use those critical values, okay? But if you implement the model using a certain package, so again, the Dickey test is called ADF test, okay? A stands for augmented one, because you want to also eliminate autocorrelation, okay, from the noise. So therefore, you have the augmented one. So Google ADF test, guys, and you Google a package, and then you can implement that. And I want you to basically test stationarity on your time series that you have. And if you find that the time series is non-stationary, I want you to test the increments of it also. So basically the time series that you will consider for your empirical work. Or you can take the ones that I gave you in a assignment 3 or something, I'm not sure. So that's sample, either of the two. Okay, but then don't use the packages. I'm going to be more specific. I just have 5 minutes left, so I don't have time to specify your new assignment, guys, but I will do it tonight. So I will shoot the video, and then you can watch it, and then you'll know what the assignment will be about. But that's going to be the next one. So you can already prepare it just by Googling ADF test, okay, because that is going to be the issue. I did it. So I did it basically in a fictive sample of 5 observations regarding the time series. Okay, so I was doing that from scratch, so you know what this is. Okay, now this series, the path of that series looks like this. Okay, that is clearly, you know, not, I mean, if it's basically a random walk, it could be a random walk without a drift, so it doesn't really matter. But the first thing that I did is considering the arithmetic mean. 10 plus 20 plus 50 plus 20 plus 0 is 100. 100 divided by 5 is 20. That should be clear. So the arithmetic mean is here. So this means, guys, that if the process is stationary, it's probably not around a 0 mean. You understand what I'm saying? It doesn't appear to be transstationary, but because there is no, I mean, okay, the issue is, guys, you have only 4 observations, okay? So 5 observations, sorry. So, I mean, it's not representative regarding basically the series. But there is no trend involved. I don't see any, at least. You know what I'm saying? So I don't consider model 3 because model 1. I don't consider model 1 because then you would have transstationarity as an alternative. I cannot see why this process will be transstationary, although it got just 5 observations. Okay, it's not being representative, of course, right? So it's going to be, if it's stationary, right, then it's not going to be stationary around the mean 0. That means probably not, right? So that means, I mean, if it would, let's say, it would evolve further downward, right? Then it could be the case. I don't know where the process would go to, okay? But let's say if it's stock prices, for example, okay? Stock prices cannot be negative, and for the mean to be 0, the process must be also negative time to time. You understand? So if every single observation is positive, then the mean, how would be the, or non-negative, let's say at least, how would be the mean be equal to 0 then? It's not possible. You understand? So if the mean is 0, then it's necessary for the process to be basically to be negative time to time. You understand what I'm saying? At least from the empirical perspective. So if I look at this path, right, I would basically pick model 2, okay, as to be the right one. That appears to be most consistent regarding the alternative hypothesis. If the process is stationary, appears to be basically to be the most consistent one with the path. Okay, but again, who knows what the process does for the next 1,000 observations, you know? So this is a speculation, guys. but that's also an issue regarding model selection. It has to be consistent with the path, more or less. You understand what I'm saying? So yeah, therefore, I was selecting model 2. Okay, now before I consider it, I'm just going to write down the observations, and I want to estimate that. Again, basically the response is the increments, okay, of the process, and the predictor regarding that model was the lagged observation, right? So the previous observation, okay? So that's it. So you need those. And if you want to basically, again, so these are you estimated from here. I mean, that's something that I do, but I want to have the phi parameter tested for significance. That one. That's the one. So if this is equal to 0, then this is equal to 1, right? Because it's just a reparameterization, by the way, so you've seen that. All right. Anyways, so yeah, and I take that model. So that's the one that I basically consider. Now you want to calculate the increments. For the increments to be calculated, you need to have basically the sample observations here for also, which basically yields that one, okay? And then you have 4 observation pairs. So if basically the series has 5 observations, then there is going to be effectively 4 observations regarding both the response as well as the predictor, you see? All right, so again, but you can also calculate the increments. So I was calculating increments, there's just a difference between them. It's simple. And now take this sample, and then this sample is the response, and this sample is the predictor. Period. And then you run a simple linear regression and calculate the test statistic of the parameter phi. Now the test statistic of the parameter phi is, of course, again, something that you can run. Right? We already did simple linear regressions. We also did multiple linear regressions, so, you know, all these things. Anyways, okay, so we did that. I did it. Okay, so if I was doing it right, let's say, I'm not sure. Sometimes I'm making mistakes. I got a test statistic of negative 1.3 approximately, which is not even close, not even for standard normal standards, right? So not even for that one. So we don't reject the null hypothesis, as you remember, because even for the standard normal distribution, the 5% quantile was negative 1.64, and now we're not even close. And for model 2, it was negative 2.9, if I coded it correctly. So we're not even close. So when you look at basically the table, okay, here are the critical values here for model 2, and then you look to test for the 5% level, it was negative 2.9 approximately, somewhere around that. So we're not even close. Okay, so we don't reject the null hypothesis at the 5% level at least, because the test statistic is greater than the 5% quantile. This is the 5% quantile of the Dickey-Fuller, corresponding Dickey-Fuller distribution. Okay, that's it. So these distributions have, yeah, these things, and yeah, that was it, guys. All right, so that's it. I did it from scratch, and that's going to be your next assignment. So either you take this sample from assignment 3 and test this, okay? So I want you to test stationarity, either from this sample or the sample that you worked with in your last assignments. You can also take that. Not the ones where I was, addressing autoregressive conditionality, but any of the sample that you worked with. I want to test stationarity. I want you to test it. And if you find that the process is not stationary, I want you to test that for the increments as well. Because if the increments are stationary from the empirical perspective, and the process is not from the empirical perspective, that is a double check. You understand what I'm saying? Okay, so you confirm that basically twice regarding the order. So I want you to establish basically the order of integration for the process as well as its increments. Okay? All right, and that's going to be your next assignment, guys. Sorry for taking your time, but since I started late, okay, due to technical issues, I hope you understand that, guys. Okay, so that was it for today. That was the last slide, and yeah, that was the last lecture too. Okay, so I wish you good luck for your exams, and hope to see you in the future. Thank you very much. Okay.